These are the notes for AP Calculus on the topic of related rates, continued. So this one says at t greater than or equal to 0, in other words, positive time like we usually have, positive or equal to 0, cube has a volume v of t and edges of length x of t. The volume of a cube changes at a rate, another word for rate of change, that's another word for the derivative, remember? Proportional, and remember when it doesn't specify, it's talking about directly proportional, not inversely, to its surface area. And then it says write an expression for dv dt using the proportionality constant k. All right, so we draw a little cube here. It's telling us the edges are length x of t, so call it x of t or just x. And it says the volume of the cube changes at a rate, that's the dv dt it's talking about, so we can say ddt is proportional or directly proportional. And remember when it's directly proportional, it means it's the proportionality constant k, or whatever letter they choose to use, in this case k, times whatever it's directly proportional to. Versus if it said inversely proportional, it'd be k divided by whatever it's inversely proportional to. Because directly proportional, when you're dealing with just positive values, would mean as one increases, the other increases in size. Or if something's negative, the other one increases in size as well. So that's why it's times. And what it's proportional to is the surface area. So if you write that S. But if the sides are x each, the edges are like x, we know the surface area of a cube, well, a cube has 6 sides, and each one, you can see, has an area of x times x squared. So that has 6, it'd be x squared plus x squared plus x squared 6 times, or we could just write that as 6x squared. Substitute that in there. So we have dv dt equals our proportionality constant k times 6x squared. And that one just said write an expression for dv dt using that property, the proportionality constant k. And then it says if the volume of the cube is increasing. Well, that basically means dv dt must be positive or greater than 0. What must be true about the proportionality constant k? Well, we can see the 6x squared, that part's always going to be positive because x is the length of the side, and squaring it keeps it positive. So in order for dv dt to be positive, it all depends on the proportionality constant k. In this case, the proportionality constant k would have to be greater than 0, positive. Similarly, if the volume of the cube is decreasing, that's essentially saying that dv dt is negative or less than 0. What must be true about the value of the proportionality constant k? The only way dv dt is going to be negative is if k, proportionality constant, is negative as well, less than 0. All right, let's take a look at part D on this one. Now it says the edges of the cube are decreasing at a rate of 3 centimeters per minute when x equals 2. So edge of the cube, remember, we're called x, so that's giving us the rate or derivative of that, dx dt. The decreasing tells us that it's negative, and in this case negative 3, and specifically when x equals 2. And what we're asked to find is what is the rate of change, in other words, the derivative of the volume of the cube at this instant. So we're looking for dv dt equals question mark. And then be sure to indicate units of measure, like we usually do. So start with the equation that relates v and x. That would be the volume of a cube. So it would just be the length times width times height, x times x times x. So volume is just x cubed. And they get our rates in there, dv dt and dx dt. We have to take the derivative of that with respect to time. So the derivative of v is 1, but then with implicit differentiation, since v and t don't match up, we need to multiply that 1 by dv dt equals the derivative of x cubed is 3x squared. Again, the x doesn't match up with the t, so times dx dt. And then we can substitute in what we know after we take the derivative. We know x is equal to 2 at this instant, and dx dt equals negative 3. So we get dv dt equals, that's 4, 2 squared is 4, times 3 is 12, times negative 3 is negative 36. And then indicate units of measure. The units of measure, units for volume here. Well, you can see x is in terms of centimeters. So volume is 3-dimensional, so it'd be centimeters cubed. Or the units for time here are minutes, so centimeters cubed per minute. Okay, let's look at the last part of this one. Now it says if the edges of the cube are increasing at a constant rate of 2 centimeters per minute. So now they're giving us dx dt. Part E is increasing, so it's positive 2. And what they're asking for is, well, what is the value of the proportionality constant k? Okay, so there we'll have to go back to our first problem here. We had dv dt equals kx squared. Okay, sorry, 6 times 6x squared. Okay. But we also know from part D that when you take the derivative volume, you get this, dv dt equals 3x squared dx dt. So those would have to be equal to each other. And like we said, k times 6x squared equal to 3 squared dx dt. And we know dx dt is 2. K times 6x squared equals 3x squared times dx dt is 2. We get k times 6x squared equals 2 times 3x squared is 6x squared. You can probably tell what k equals right now. But mathematically, to solve for k, you divide by 6x squared. And you end up with k, the proportionality constant would have to equal 1. Okay, let's take a look at another example. This one says the volume of a particular cone for which the sum of its radius and height is constant. Okay. How about where that's coming from? Was 1/3 pi r squared times minus r. Well, no, in the volume of a cone formula, usually what's right here, this whole expression right here, is usually the height, h, 1/3 pi r squared. Well, why don't we see the h here? Well, they're already doing something for us in this. It'll make it a little easier, actually. They say the sum of the radius and the height is a constant. In this case, the sum means we're adding. So they're saying the sum of the radius and the height is a constant. And what that constant is in this case is the 12. You can see from here. Because then if you solve this for h, if you subtract r from both sides, you end up with h equals 12 minus r. You can see they've already done a substitution for you, substituted in 12 minus r for it. So that's where that's coming from. Now, let's see what we're asked to find and what we're given. So it says the rate of change or derivative of the radius of the cone with respect to time is 4. So that's given us the rate of change of the radius, dr dt equals 4. Then it says in terms of r, that means our answer's going to have on it, what is the rate of change of the volume of the cone with respect to time? So we're looking for dv dt. And it says in terms of r, so we're not going to expect to get a constant for our answer. Variable r. Okay, so we've already got our equation given to us that relates v and r. So we could take the derivative right now, but notice if we did that, we'd have to use the product rule to take the derivative, because we have the 1/3 pi r squared times 12 minus r, which you could do. But in this case, it's probably a little easier if you actually just distribute that 1/3 pi r squared out before we take the derivative. And that, well, you will no longer need to use the product rule. So the volume will equal 1/3 pi r squared times 12. Well, 12 divided by 3 is 4. It'll be 4 pi r squared minus 1/3 pi r squared times negative r is 1/3 pi r cubed. And now let's take the derivative of that with respect to time to get our rates in there. The derivative of volume, dv dt, equals the derivative of 4 pi r squared using the power rule. Bring down the 2, so that'd be 8 pi r times dr dt. And then the derivative of negative 1/3 pi r cubed, bring down the 3. 3 is reduced out, 3 divided by 3 is 1, so just be pi r squared times dr dt. All right, and then we can substitute what we know. So we have dv dt equals 8 pi. We aren't given r, so 8 pi r. Remember, our answer is going to be in terms of r, but we are given dr dt as 4. I'll substitute in dr dt as 4 for both of these. So we get dv dt equals 4 times 8 pi r, 32 pi r. 4 times negative pi r squared is minus 4 pi r squared. Notice we're not given any units in this problem, so we can't put in our answer. If it was like inches, it would be inches cubed per, if it was seconds per second, whatever, would give me units for anything on this problem. But our answer, notice, is in terms of r, so that would be our answer for dv dt. Take a look at one more different example. This time we've got a sphere. So if we start out with a circle here, and let's make it look spherical. So we can by trying to draw a little cross section right at the equator, I guess you could say, of the sphere. Then it says a sphere is expanding in such a way that the area of any circular cross section through the sphere's center. Okay, so if this is the center of the sphere right here, and there's our radius, it's Let me try to draw it better. There's the radius. We can call R. Then it's saying area of any circular cross section, this is the area through the first center, is increasing at a constant rate of 3 centimeters squared per second. So they're giving us dA dt. It's increasing to positive. And then it says at the instant when the radius of the sphere is 5 centimeters, what is the rate of change of the sphere's volume? So it's trying to find the rate of change of the sphere's volume. Specifically when the radius is 5. And this time we are asked to indicate units of measure. So let's start with what we know. Well, in this case, there's not really an equation that relates easily. You would know off the top of your head usually to the volume of the sphere to the area of the circle. So let's start with the formulas we do know. Volume of the sphere, remember, is 4/3 pi r cubed. So since we're looking for dV dt, let's start with that one and take the derivative of that. So derivative of v is dV dt. The derivative of this one. Bring down the 3, reduce out, so it's 4 pi r squared times dr dt. And then we can substitute in what we know. We know r is 5. But we don't know dr dt yet. So since we're missing dr dt, let's see what we can do to figure it out by utilizing the fact we know dA dt is 3. Well, that represents the rate of change of the area of the circle. We know the area of the circle formula is just pi r squared. So sorry about that, I accidentally hit the wrong thing there. So if we take the derivative of the area, that'd be dA dt equals derivative of pi r squared is 2 pi r dr dt. And since we know dA dt is 3, and we know r is 5, we can use this equation to help us solve for dr dt. We've got 3 equals 5 times 2 pi is 10 pi dr dt. And when you divide by 10 pi, you end up with dr dt equals 3 divided by 10 pi. And that was our one missing piece of information to help us find dV dt. So we can substitute that in right there for dr dt. Now that we know that is 3 over 10 pi. So you can see right here the pi's reduce out. And I'll simplify what we have left here, dV dt. Well, 5 squared is 25, times 4 is 100, times 3 is 300, divided by 10 is 30. And the units for volume, since area is in centimeters squared, this would be centimeters cubed. And since time is in terms of seconds, it would be per second. And that concludes the notes for AP Calculus on the topic of related rates continued.